So in this lecture, we talk about logistic regression, okay? So we have already talked about linear regression, where we find the least square regression line to, track one or more variables, where there are one or more, independent variables. And based on that, we predict the value of a dependent variable. So now from linear regression, we come to logistic regression. What is logistic regression and what it is being used for? We'll talk more about it. So linear regression is mostly used for continuous numeric value prediction. Okay, if you remember that we used to used to predict house prices from the square footage of a house has. Okay, so this is more like continuous value prediction. So that the line of the prediction line or the linear regression line kind of spans from minus infinity to plus infinity in that range. Okay, so but logistic regression is a little bit different thing. Okay, it's a probabilistic categorization of variables. Okay, probabilistic categorization. So how it works? So there will be two categories, yes or no, or we call it a class 1 or class 0. So if, let's say, that for a particular variable the value is higher than 50%, the predicted value, then we say, okay, it belongs to class 1. And if the value is less than 50%, then we say it belongs to class 0. So we have, it's not a continuous continuous value prediction. It's predicting classes either 1 or 0. So there are only two classes. Sometimes logistic regression can be used for, multi-class prediction, but in general, logistic regression is more suited for binary classification. When logistic regression is being used for multi-class classification, there'll be some special techniques we'll talk about later. They can be used and the problem can be broken into multiple smaller binary classification problem. But otherwise, logistic regression is best suited for binary classification. And here we talk a little bit about the classification problem types. Okay, so as I said already, binary classification is where, based on some numeric attributes, can we predict whether, like an example, a consumer will buy insurance or not. So that's a yes no kind of answer. Okay, yes is a category 1 or class 1, and no is category 0 or class 0. Okay, so multi-class classification is like can be under different circumstances. Here one example is, given some attributes, maybe some numerical attributes, can we determine if a particular stock is buy, sell, or hold? So you have to categorize it either as a buy or as a sell or as a hold. So there are three different classification. Okay, so other things can be like, given an image, can a machine learning system identify it's a dog or a cat or an elephant, something like that. So you have to know those classes from the beginning. So, as I said, logistic regression is a class of binary classification problem, and we'll learn more about it. Now we want to show what logistic regression really does, or how it works. So you see, if there is a data set which kind of tries to predict whether how the person, based on their current age, whether they will buy insurance or not. So from previous records, you can see that, okay, at 20, 30, 40 early stage of the life, people do not really buy insurance. So this is bought insurance. 0 means they did not buy insurance, or they are not buying insurance. 1 means they bought insurance. So red dot means they did not buy insurance. Green dot means they bought insurance. So there are some people who at the early stage of the career or life buy insurance, but mostly people at a later stage of life, they buy more insurance. So if we use a linear regression model into this and we draw a line, now if you see that if we are trying to find out that classification perspective, that if it's more than 0.5, can we say that they bought insurance? I mean, it's less than 0.5, we say that they did not buy insurance. You can see here, if it's less than 5, we can generally say that, yeah, they did not buy insurance, so this the prediction fits. But if there is a more than 5, so from this line, the right side, yes, they bought insurance, so the prediction fits as well. But there are some lines on the left side of that 0.5 line, and then we can see that there are still some people who bought insurance, but they are not really covered, which are very close to this line. They are also being missed by this linear regression. So linear regression does not seem to be a very good fit. We cannot really two groups of points, we cannot really separate always with a single line. So what we are trying to show here is that can we use a different function like a this is called a logit function or a sigmoid function, and the similar kind of data, similar kind of graph, a logit function kind of maps much better way than the linear regression, the least square regression line. And we can find that this is a special function, sigmoid or logit function. This function can be represented in this way, that 1 over 1 plus e to the power minus y. So here E is Euler's number, which is an repeating non-repeating number which never ends. Okay, so this the first few digits are 2.71828 dot dot dot. This is also used as a base of the natural logarithm. We have to remember that, and we'll come back to it. We'll use that to show that how it works. So what does it do? It actually converts an input into 0 and 1. Okay, so if something is above 0.5, then it will identify it as 1. If it's something below 0.5, it will identify it as 0. And you can see that this, how I relate this to equations is the equation of the line where for the linear regression, this is the equation where y is 1 over 1 plus e to the power minus mx plus b. Here, this value of y, we replace this with the mx plus b so that we kind of twist that line and then find the bias and the slope or the intercept and the slope, and then put it here to get what will be the prediction of the value of y using the logit function. We want to talk a little more about the sigmoid function, because sigmoid function is something which will come back again when we talk about activation function in neural network, and it's a very important function. So let's talk a little more about it. Sigmoid function, which is also written as a sigma, and a sigmoid of z equal to 1 over 1 plus e to the power minus z. The domain of this function is minus infinity to plus infinity. All the independent values can take from minus infinity to plus infinity, and the dependent values will have range from 0 to plus 1. Okay, so how the 0 to plus 1 thing works, let's see here. So using limit z tends to minus infinity, e to the power minus z is plus infinity. Limit z tends to 0, e to the power minus z equal to 1, and limit z tends to plus infinity, e to the power minus z equal to 0. Okay, so plugging in those values in this expression, sigma z equal to 1 over 1 plus infinity equal to 0, but putting infinity in equation is not a very good thing, but just try to show you the idea, the concept. And sigma z equal to 1 over 1 plus 1, which gives half, and sigma z equal to 1 over 1 plus 0 equal to 1. So it varies from minus infinity to plus infinity, which is giving the range of 0 to 1. And this is sigmoid function. And we'll talk more about how logistic regression come to use this sigmoid function as the best function in the next video.